So for those of you unfamiliar with mass timber, I promise you it's coming to a neighborhood or a community very close to you. Over the next 20 minutes, I'll take you through the last several decades of NARI and the predecessor NIS from the view of the mass timber revolution. So imagine you're sitting down at 6 a.m. for breakfast. You just moved into your 6-story condominium or apartment complex in the US, and you're living in Southern California, and you're scrolling through your social media, and you're just about to drink your cup of coffee, and a 2,500-year earthquake strikes. So this is what it feels like inside, or this is what it looks like inside, but this was 2009. This was at the Earth Defense Laboratory in Miki City, and this was a 2,500 year, for those of you that scale earthquakes, 180% of the Canoga Park event. It still remains the largest shake table test ever conducted. So in 1989, while the World Series was underway at Candlestick Park, and many of you remember that if you're over the age of 40 probably, and an earthquake struck in 1989 named for Loma Prieta Peak in the Santa Cruz Mountains where the epicenter was. It collapsed the top level of a freeway, and I think many of us remember that was when cell phones were actually in cars, and people were calling to be rescued from the wreckage, the people that had cell phones in their car. But it also destroyed many, many soft-story wood frame buildings and brought to light that crisis. 5 years later, a blind thrust fault about 450 miles away in Southern California produced the devastating Northridge earthquake with obvious widespread damage. But there was also damage that wasn't quite as evident. And so born were two major research efforts, the SAC Steel Project for steel frame buildings and the Curie-Caltech wood frame project. So as a direct result of the Northridge earthquake, the Curie-Caltech project, it took a really long and a hard and honest look at the deficiencies in wood frame construction in the US. Historically, we thought it performed very well, and it did, relatively speaking, because it's light, and so it doesn't generate a lot of forces. But many, many key recommendations came out of that. So following the smaller groundbreaking tests, and these were the truly groundbreaking tests as part of the Curie-Caltech project, many of you or some of you were probably part of those. But one of the index buildings that was designed as part of that effort was then tested. It was the first major test that used both shake tables at the State University of New York at Buffalo NIS laboratory. Now, that particular test was led by co-PI Andre Filiatreau, who many of you know. So the Earth Defense Laboratory in Miki City, Japan, it was built about the same time as the NIS network. It was completed in 2004, and it was the Japanese government's direct response to the Kobe earthquake that occurred almost to the day 1 year after the Northridge earthquake. And quite honestly, the Kobe earthquake, the Japanese government felt that the level of damage and the number of deaths that occurred for a country with such stringent building codes, seismic building codes, was unacceptable. And so this facility was built. It's 10 stories tall with a 6-story door to bring specimens in, provided they're under 6 stories. It's a 15 by 20 meter shake table. So in February 2009, the NISwood team, and this was funded, but we were funded by the National Science Foundation under the NIS program, operating at eDefense through a memorandum of understanding between NSF and Japan's MEXT, which is a very long acronym I can't remember, but many of you know it. And it began construction on what would be the world's largest shake table test, as I mentioned, applying information from post-Northridge and from numerous labs around the US, not NIS tests as well as others. So the building was designed using a new philosophy. At the time, it was relatively new. It was definitely new for wood, and that was performance-based seismic design. But what became notable was that portions of the buildings started to look more like solid wood and not light frame wood construction. And so this, what you see behind me is a stud pack, and there's one about 6 feet away on the other side of the wall. There were massive walls to resist earthquake load. This was through a partnership with the Canadian government and Canadian industry in Canada. And several years later, the NIST-funded team used software that was developed as part of this project to perform analysis and work with the Canadian government at their request to increase the allowable wood frame height for the National Building Code of Canada from 4 to 6 stories. And so NSF-funded research through NIST and through the networks directly changed the building codes, as I'll get to in a moment, in the US, but not just the US, but also in other countries. So a team of almost 60 damage inspectors, about half of them from nearby Kobe University, worked rapidly following tests on the 6-story performance-based seismic design building. From the NSF-funded project, you heard about Elena, but there were multiple academics born through each of these projects, including the project that I'll go through at the end. And many are conducting NSF-funded research right now through other, all around the US as well as in other countries. So remember, you were drinking your coffee, relaxing, and it looked bad inside. But now let's take a look at the outside of this 6-story building. So this is the same shake that you just experienced. You did have to change your shirt because you spilled your coffee, but there's no doubt about that. And as you'll see from this, the building response is excellent. This is maybe a second mode in there, but it's designed using direct displacement design. It was and so what you see here is drifts of only up to a couple of percent at each story, and this was the stronger component. So remember what you just saw, that was a 2,500-year event. You're not supposed to experience that. So soft-story wood frame buildings around the U.S., U.S. and the world, they continued to be a problem. Here behind me you see photos. I think I took one in New Zealand in 2011. There's one from Loma Prieta that's been on the cover of ERI documents, things like that. And this is really what they look like. So the result of performance-based retrofit approaches were tested over the course of a month or more in San Diego. And the performance was perfect. As you'll see here, you'll see a second mode, and it's a quick shake. It's Loma Prieta. There's only 12 seconds of strong ground motion, but it's a strong event. And so the NIST-funded student that you saw just stand up in the foreground with the green hard hat, he was pretty excited. That was our first MCE shake. And he is now an assistant professor at Washington State University in his 4th week. And working with us to change building codes for cross-laminated timber, or at least introduce it. So one of the major takeaways from collaboration with Japan over the years, it was really one thing that we learned, that the e-defense table, they were the first table that could really collapse buildings realistically, at least wood frame buildings. And so one of the major takeaways that we learned was that in models, forces provide the displacement, but the models don't always predict collapse. And what we're really doing is we're pulling the rug out from under these. And so what you see behind me, this is of course with no retrofit in place, otherwise I wouldn't show you a collapsed building if I retrofitted and it collapsed. And so the results of these tests, and this is another video in the back. You got it, if you got that. Okay, thanks. And so the results of these provide validation of some of the most advanced models, numerical models ever developed. And so For wood frame buildings. And those numerical models, they're being used right now in collaboration with the Applied Technology Council, FEMA, NIST, by former students who are professors themselves, and they're working to calibrate codes. And so I know it looks bad, we collapse buildings to learn, that's all. So pictured here is the majority of the NIST team. This is the San Diego-based NIST team. Elena was testing at Buffalo, Elena Sutley that you heard about on a test. We actually, because of scheduling, we wound up doing 2 full-scale tests simultaneously, one on the East Coast, one on the West Coast. So anyway, I'm a frequent flyer on United now. So pictured is the NIST team, as I mentioned, industry collaborators, a lot of industry collaborators. As well as faculty, and then just 2 of the students right there are professors at Alabama and, as I mentioned, Washington State. And then 1 professor shown in this that was a co-PI on NIST was a student on NIST-Wood. So we actually have now 4 generations just from NIST and Nehari as of Washington State just days ago. So we're really excited about that, and to show kind of the power of bringing that forward. And so as I mentioned, this software, it's allowing us to add new engineered systems to codes. So now I want to turn your attention to mass timber itself. So mass timber is arguably, and I would argue it, it's the most sustainable construction material on Earth. It's one product in particular has led the way, cross-laminated timber. It's fairly widely known as CLT. It originated in Europe in the 1990s. In fact, about 2 months ago, I was in Slovenia, where much of this testing originated, and for a conference called Woodrise there that's every few years. And so it worked its way west into Canada first. We worked with the Canadians for a while, and then moved into the U.S. And now there's plants popping up all over the U.S. And in fact, that in NIST, the CLT retrofits that we did that were mentioned by Tracy, that was actually, we had to import that from Europe just in 2013. And so the material itself has superior fire suppression. It's sustainable. It's very rapid. It goes up. It's really just the behavior is in the connectors. So CLT was active through a large project also funded by the Italian government with tests conducted at multiple labs. They tested at eDefense right before we were there, as well as other labs. It's now moving forward in Japan. In Japan, you're only allowed 3 stories of wood construction due to fire and other concerns. But my math's not that great anymore, but it looks like 5 stories there. And so I think it's really just a matter of time until 5 stories of mass timber construction is allowed in Japan as well. So almost 1,200 major CLT or mass timber projects were underway in 2021 in the U.S. There's 1,500 currently underway right now, and at some point, the goal is to lose count. So it's hard to know what sparks change or what sparks a revolution really or anything. Sometimes we see that point in time and sometimes we don't, but we know it takes ingredients, and in this case, it's ingredients a couple of decades in the making. With sustained effort by a large group, far, far beyond what I've been part of. But it's a network of people, and it's a network of equipment that enables people to create the conditions necessary to evolve or to have a revolution. So beginning in the late 90s with the Curie Caltech project, and then NIST-Wood, the NIST-Wood project made possible through the shared use NIST facility, NIST through the same network. And so, as I mentioned with the 4 generations, the student becomes the teacher. And so I think that something like this is really only possible through a shared shared use network like this. And so for all of you out there that are assistant professors and you've not done a project, neither had I when I got NIST-funded. I hadn't done a big project, so go after it. And so many other people over a host of other projects have contributed to this revolution, some through the network, some in their own labs. We like to think we had a little something to do with it, but we know the networks did. And so I just want to show a couple of videos of some recent testing. This is 2017 project led by Shilang Pei. And this is the NERI Tallwood project. It doesn't look like a tall structure. It was a test of opportunity at UC San Diego's NERI facility in 2017. And you can see excellent performance. This right now, this is actually, this test helped bring cross-laminated timber into U.S. building codes, and so it's now in ASC 722. Still needs some work, but it's there. And I'll jump to the next. Did I do that? Yeah. You can jump to the next slide if you like. I think my pointers. And then that's a video also. And so this is the post-tension rocking wall system that was tested also as part of that project. And so what you'll see here is you'll see excellent performance. This building, the idea is resilient mass timber construction. It went through 25 earthquakes, including about 6 or 7 MCE level. Jeff probably remembers how many. Yeah, so. And you can go ahead and go to the next slide, if you would. Thank you. So the Tallwood Design Institute in the state of Oregon it was founded in 2014. And this is just an example, one example of literally tens, if not maybe 100 institutes and centers that are popping up all over the world. And they're in 20, 30 more countries, all through South America. South America typically uses mostly concrete construction. They're starting to build and want to build with mass timber. So under construction now is a 10-story full-scale mass timber building. It has 4 mass timber post-tension rocking walls, 2 cross-laminated timber in one direction, and 2 mass plywood panels in the other direction. Just a different technology, but it's all mass timber. Tallwood is led by former NIST-funded student Shilang Pei, a professor at Colorado School of Mines, and this will be subjected to more than 20 earthquakes, including at least 5 MCE or 2,500-year events. And ultimately, the top 4 stories will then be removed, and another NERI-funded project led by Andre Barbosa from Oregon State University is developing a new converging design philosophy, and they'll apply that to that, and that includes the things like keeping affordable housing as well as other things. And so it's a very, both very groundbreaking in the sense of taller wood frame or wood construction. And so just some images. This is happening right now. They're probably actually on site trying to do construction right now. And then this is the video, if you could start it about a quarter way through, please. So this is some drone footage from just about 6 days ago. And so this is at almost 8 stories. Networks are about they're about equipment, and they're about the people that form the teams around them. And so on behalf of the entire Tallwood team, and I think Jeff Berman is one of the co-PIs with me as well, and so I just want to acknowledge him as well. But on behalf of the entire Tallwood team, you're all invited to the world's tallest shake table at 112 feet into the air in the beginning of 2023. And it represents the future of sustainable and resilient construction. And we can probably jump to the next slide. There's a massive timer up here, just so you guys know. So, it's right there. And so, mass timber is green, it's resilient, it's energy efficient, it's easily constructed and rapid, but most importantly, it's sustainable. And so, coming over the next decade for, I don't know what we're calling it, Dan, I don't know what you threw something out there yesterday, but coming in 2026 to 2035 over the next decade, it'll be multi-hazard designs, sustainable and climate adaptive designs, and then not just tall, but true high-rise mass timber buildings. And so with that, lots of acknowledgements, and I encourage you to go to the webpage and see them. But with that, it's a pleasure to be here and to see all of you. Thank you.